Imagine you need to hit a series of APIs, 100 of them in total, and return all the results. That's a pretty common scenario in development. How would you handle it? The classic solution is to loop through them with a for loop. But if you time the program using the time module, you'll find it takes a full 79 seconds. And that's only for 100 APIs. In real projects, you might be dealing with 1,000, 10,000, or even 100,000 of them. So what do you do then? What we really want is a faster program. And this is where asyncio comes in. It can significantly improve the performance of IO-bound programs. For example, when I rewrote the program using asyncio, it finished the entire job in just 13 seconds, more than a 6 times speed up. And I can tell you, as the number of API calls grows, this advantage becomes even more pronounced. So how does this powerful tool actually work? Let's take a look. At its core, asyncio uses something called coroutines, which are basically Python's way of doing asynchronous programming. It manages everything using an event loop and a task queue. The queue holds all the tasks that are ready to go, and the event loop constantly grabs tasks from that queue and gets them running. A coroutine itself is just the execution list for one of these tasks. It's essentially the code. Right now, how coroutines work probably sounds a lot like a normal loop. But here's the special sauce. Asyncio is fantastic at handling I/O operations like network requests or reading files. The thing about these tasks is that the program itself doesn't actually need to do the work during the runtime. For example, with a network request, most of the work is being done by the internet, not your CPU. So it's incredibly inefficient for your program to just sit there doing nothing while it waits for a result to come back. It's like how you wouldn't just stare at the screen while a game is downloading. You'd go do something else instead. So, with asyncio, when a coroutine hits an I/O wait, it suspends itself, and that task is taken off the queue. This frees up the event loop to go run other waiting tasks in the meantime. Once the I/O operation is finally done, the coroutine puts itself back on the queue to be scheduled again. Get it? The program's total runtime just eliminated most of that wasted time spent waiting for I/O operations. So naturally, the program speeds right up. So that covers the basic idea. Now, let's get to coding. To really master asyncio, you need to understand the main players. Coroutines with the async keyword, awaitables with the await keyword, and task objects. Let's start with the absolute simplest program. The first step in writing an asyncio program is to create a coroutine. In Python, a coroutine is simply a function that has the async keyword slapped in front of it. When you call this function, it returns a coroutine object. But be careful. Unlike a regular function, it doesn't run immediately. For example, the print statement we write won't show up in the terminal yet. To actually make a coroutine execute, we need to wrap it as a task, put it into the task queue, and introduce it into the event loop scheduling process. You do this with asyncio run main. What that function does is call main to get the coroutine object, and then asyncio immediately wraps it as a task, puts it in the queue, and starts the event loop. And just like that, our first coroutine runs successfully. Now, how do we make the program a bit more complex? How do we add more tasks? A straightforward way is to use the create task method. Let's say we write 2 extra coroutines, and we want our main coroutine to add them to the task queue while it's running. We just use create task on both of them. Then these 2 coroutines will be added to the task queue. When our main coroutine suspends, coroutine 1 and coroutine 2 will run sequentially. You may notice that I added await sleep 5 here. Its purpose is to suspend the main coroutine for 5 seconds and remove it from the active task queue. This allows the event loop to schedule coroutine 1 and coroutine 2. Consequently, while main is suspended, you will see the print outputs from coroutine 1 and coroutine 2 appearing one after another. But wait a minute, how exactly does the coroutine suspend itself, like we talked about earlier? This is where await makes its grand entrance. Await is the suspension point. It temporarily hangs up the current coroutine and kicks off the object it's waiting for, staying suspended until that object is done. If the object being awaited involves an I/O operation, like a network call, the current task won't use the CPU while it waits. This frees up the event loop to switch gears and schedule other tasks that are ready to run, dramatically boosting efficiency for IO-bound programs overall. For example, if we put await sleep 1 inside coroutine 1, when execution hits that line, coroutine 1 gets suspended, removed from the task queue, and it waits for a 1-second timer to finish. Just like an IO operation, running that timer doesn't require our program's CPU, so the CPU goes idle. The event loop sees this opening and switches to run coroutine 2. When the 1-second timer finishes, coroutine 1 puts itself back into the task queue, and the event loop schedules it to pick up where it left off. With this principle in mind, let's look at a classic asyncio example of speeding things up. We'll add await sleep to both coroutine 1 and coroutine 2. Here's the play-by-play. Coroutine 1 hits await, suspends itself, and starts a 1-second timer. Since the timer is running off CPU, the event loop is free, so it runs coroutine 2. Coroutine 2 also hits await, suspends itself, and waits for 2 seconds in the background. 1 second later, coroutine 1 is ready first and resumes running. 1 second after that, coroutine 2's result comes in and it's ready too. Because they ran concurrently, this program won't take 3 seconds to run. It only takes 2 seconds. When you apply this to a much larger list of tasks, like making network requests, the time needed for those requests usually far outweighs the time it takes for your code to execute. This means your final time will largely depend only on the single longest request, not the sum of every request's time. Besides speeding things up, await has another main job, collecting the final results from different tasks within the same main task. Up until now, we haven't made our tasks return actual values. Of course, you can do that, but the question is, how do you grab the value? The value actually gets passed through the task itself. But you can't just read the task right after creating it because it might not have the result yet. You'd get an uncertain result. The solution is to use await again. The mechanism is this. When main hits the first await, it suspends itself, waiting for the result of coroutine 1. Once coroutine 1 finishes and returns the value, main grabs that result and puts itself back into the task queue. Then, it immediately hits the second await, and similarly, the result is fetched. That's how the results from 2 independent tasks are collected, one after the other. Adding multiple tasks to the queue all at once is obviously something you'll do a lot. Luckily, asyncio gives us some handy tools for this, like gather. This function lets you run a bunch of coroutines simultaneously without having to create a separate task or write a loop for every single one. It saves you tons of repetitive code. With gather, you can kick off multiple tasks at the same time and then deal with all the results in a unified way once they are all complete. It's perfect for concurrent IO or handling batch jobs. If you keep learning asyncio, gather will probably be the function you use the most. You also use await when you need to get the results from coroutines in a specific order. For example, here's a super common situation. You have 2 coroutines, and coroutine 2 needs the result that comes out of coroutine 1. So you'd write it like this. The way this works is that main hits the first await, suspends itself, and waits for coroutine 1 to finish. Only after that's done does it continue to the next line, where it hits the second await and hangs up again, waiting for coroutine 2 to complete. Notice that coroutine 1 and coroutine 2 here are just execution steps with main. They're running one after the other. And in this scenario, asyncio won't give you any speed boost, even though it's still using coroutine technology. Coroutine 1 and coroutine 2 are completing sequentially. So I hope you understand now. Asyncio doesn't always speed up your program. It only works if you use it correctly. Specifically, the real speed comes from using create task to add multiple IO-bound tasks to the queue all at once, letting them run concurrently.